we've talked about charging objects up by rubbing them, but we need another way. We are now going to talk about charging by induction. This is something we can do now that we know we have two kinds of materials. So one material will be our charged insulator. It could be the Teflon rod. So we know if we take the Teflon rod and we rub it with the fur, we get negative charge on the surface. So the insulator gives us a way to just hold a charge somewhere. Now the other object that we want to bring nearby is a neutral conductor. And as you know, when I talk about a conductor, I almost always talk about a metal. So let's assume this one is a metal. So now, since it's a metal, we'll think microscopically what's happening inside. So we know in this metal, it's full of free electrons. Say here's an electron, it's got a negative charge, it's just sitting there minding its own business. However, we bring this charged insulator nearby, all these negative charges. It's going to feel a force due to Coulomb's law. It's going to feel a force this way. So it's going to accelerate that way, it's going to move that way, and it wants to get as far away as it can from these. It's always going to feel a force. It's going to go until it gets right here. And then it can't go any further because it can't leave the material. Now, what's left here though? Let's think for a second. What's left here? What's left here is a place where there used to be an electron and now it's missing. So that nucleus, that atom, is net positive. So you actually leave what we call in physics often, we call it a hole in the material, in the metal. It's a place where the electron was to keep things neutral, now it's gone. Well, that hole isn't just going to sit there. You can think of that hole as a positively charged particle. Actually, you could imagine that hole is a positively charged particle that's going to come over here. Or you can say these free electrons, they want to get away too, but if they move a while, they might see that hole. And they'll say, oh, okay, I'm going to go there. And that's going to take that thing away, but now we have a hole here. So you can think about imaginary positive particles called holes. You can imagine refilling the holes left by the electron that moved. You can think about it however you want. Ultimately, though, you get positive charge on this side. Okay? It was neutral. You move some excess charge over here. You leave positive charge over there. And a bunch of charges will do this. A bunch over there. A bunch will build up opposite amount over here. So now this conductor is polarized, is what we would say. The charge has been polarized. It's been pushed to the two poles. We have a negative charge over here, positive charge over here. So now, to charge by induction, all we have to do is one thing. We cut it. With the negative, or with the negatively charged insulator here, we just cut it in half. So let's cut it in half into two pieces of metal. And this is still here. Okay. So the charges don't have any need to go anywhere. They're happy where they are. But because of the way it's all set up, and with this still here, you end up with positive here and negative here. Okay. All we did was make an imaginary cut right in the middle. And now, though, you can see, even when this is gone, now each half, oops, has equal and opposite charge. So now they're both charged. In fact, we charged up two things. We charged up this piece of metal positive and that piece of metal negative. Now in the real world, you don't charge by induction by cutting pieces of metal. Cutting metal is very hard. There's other ways that you do it. Here in this demo, we're going to charge these two spheres by induction. So the two spheres are the piece of metal. And we have them touching right now. And electrons can easily move from one to the other when they're touching. So it's essentially one piece of metal. But later when we move them, that's a way to cut them. We don't really have to cut them. We just have to separate them like that. But when they're touching, the conductance across that gap is pretty good. So we think of it as one piece of metal. I'm going to bring my Teflon rod, charge it with fur, bring it close, and it's going to create a separation of the two charges, or of the charge in the metal. So if I do this, here's a negative charge, I bring it right here. It's pushing negative charge over here, and it's leaving positive charge over there. Okay? You didn't see anything. Well, there's nothing to see. All right. So let me charge it up again, bring it over here, and now I'm going to cut. I'm going to separate them. And now we just charge the two spheres by induction. And of course, you can't see it. I'm going to try to prove it to you with a little bit of Teflon tape. All right, so we know if we rub fur on this Teflon tape, we know it ends up negative. So if this thing ends up negative, then they should repel each other, or the tape should be repelled. And sure enough, you can see the tape is repelled. Doesn't want to touch the metal. And we should have left the other one positive. Oh, and sure enough, it's positive. It's very sticky for the tape. Okay? So we can use our Teflon rod, or our Teflon tape, to confirm it really did what it was supposed to do. Repulsion there. There's one other way we can confirm it, is when I bring them together, if you look very close, you can see a spark jump across the gap. The negative charge, the positive charge comes back together, makes a corona and an arc like we talked about before, and you can actually see the charge go back. So seeing is believing. And there it was. Okay, so charging by induction. It's also not a quantitative thing like rubbing. We aren't going to calculate the amount of charge that we pushed around. Maybe we can do that later. But for now, it's just another way to think about how charge behaves in a material.